Alright, let's move on to number 4. We need to differentiate f of x with respect to x. Well, it's not in a form ready to differentiate yet, because I've got the x's in the bottom. And so the first term doesn't change, but I should bring my x squared up to the top where it becomes an x to the negative 2. So always rewrite your function in a more friendly form before you differentiate it. On the next step, this is where we begin the differentiation. So there's my f prime notation. The derivative of 3x is 3. And the derivative of the second expression, well, the 12 hangs out in front. The negative 2 exponent moves in front to join the coefficient, and it becomes x to the power of negative 3. If I simplify this expression, I get 3. 12 times negative 2 is negative 24, and my x to the negative 3 I can move down to the bottom, where it becomes an x to the positive 3. IB won't deduct marks if you don't move your exponent down, I don't think, but I like to move it down because it's much easier to substitute into something which does not have a negative exponent. So in part B, I need to calculate f prime of x when x is equal to 1. So I'm going to substitute 1 into the derivative function. I've got 3 minus 24 over 1 cubed, and that equals negative 21. So that's my derivative when x equals 1, which of course represents the slope of the tangent. You can see that the slope of the tangent is negative, so it's obvious that we are decreasing. So at x equals 1, we see that the derivative is less than 0. It's negative 21. And any time that your derivative is less than 0, that represents a negative gradient, a negative slope, and so therefore we are decreasing at x equals 1. And of course, if the derivative had been greater than 0, then we would have been increasing. Okay? Moving on to part D, I need to solve the equation of f prime of x is equal to 0. So remember that f prime of x was equal to 3 minus 24 over x cubed. And so we'll set the derivative equal to 0. And I can solve this one algebraically easily enough. The negative 24 over x cubed moves to the left. Multiply both sides by x cubed. Divide both sides by 3. And now I can take the cube root and I'll find that x is equal to 2. So there's only one spot where the function's gradient or derivative is equal to 0, and that occurs when x is equal to 2. That must be either a maximum or a minimum. Now in part E it says that the graph of f has a local minimum at point P. Well, we've found the only stationary point. The only stationary point is when x is equal to 2, so I guess that must be a minimum. But we can verify that first. Let's draw a sign chart, and our only stationary point is 2. I do want you to look out for another spot, though. If you look back at the original function, check out the x squared in the denominator. Anytime that you have an x squared in a denominator, or an x in the denominator, or an x cubed, anytime you see an x down at the bottom of one of the terms in a function, that means that we have a vertical asymptote at x equals 0. So I'm going to add this to my diagram here. At 0, I have a vertical asymptote. Okay? So I now have actually 3 different regions that I need to test. Let's test something to the left of 0 to see whether I'm increasing or decreasing in that region. So I'll put in negative 1. If I substitute in negative 1 here, so 3 minus 24 over negative 1 cubed, if I evaluate that, I'll end up getting a positive value. If I substitute in something between 0 and 2, let's say like 1, so 3 minus 24 over 1 cubed, I get a negative value. And if I substitute in something on this side of 2, like 3, 3 minus 24 over 3 cubed, I'll end up getting a, positive value, right. So now you can see the picture of the graph. We're first increasing, and then we approach an asymptote. Then we're decreasing on the other side of the asymptote, and I hit a stationary point which is flat at 2, and then I'm increasing. So there you go. Now you can see that there is a minimum at x equals 2. So in E, part I, it says write down the coordinates of P. Well, obviously the x-coordinate is 2, because it's a minimum, the only stationary point, and to find the corresponding y value, we need to substitute the 2 back into our original function. So f of 2 is equal to 3 times 2 plus 12 over 2 squared. And that gives me 6 plus 12 over 4 equals 3 equals 9. So my point P is at 2, 9. Now we've got T, this tangent, at point P, so I'm just going to draw in a different color a diagram of my tangent line. Obviously it's a flat tangent line, isn't it? Because we're at a local minimum. And if it's a flat tangent line, then clearly the gradient of line T must be 0. Okay? So a 0 is the gradient of T. And lastly, we need to write down the equation of T. Well, the equation of a horizontal line is really easy. It's always y equals something, right? Just like a horizontal asymptotes equation is y equals something. In this case, your y is going to equal, well, whatever the distance is to the line. And we know that point P is 2, 9. So clearly the y-coordinate is 9. That must mean that the distance upwards is 9. And so your equation for line T is y equals 9. Another way you could have found that would have been by substituting into y equals mx plus b, and we've got 0x plus, and then you'd have to figure out what b is, and you could substitute in your known point P, 9 equals 0 times 2 plus b, and you realize that b is equal to 9 that way. So y equals 0x plus 9, ergo y equals 9. Moving on to part F, we need to sketch a graph of this function. I'm just going to recopy the function for myself. So it's f of x is equal to 3x plus 12 over x squared. Alright, so let's sketch a graph of the function. I can see that I've got a width of the domain of 9 units, and then I've got a width of the range is 22 units. I've already set up my graph paper ahead of time, so it's exactly 22 centimeters tall. And so obviously it goes all the way up to 15 and all the way down to -7. And so let me just put in my x-axis on that basis. I know I've got 15 units that are above. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. So here's my x-axis. Sorry, I really should draw this with a ruler. Don't forget to label your axes as you go. And then we've got our y-axis. Well, I set up my graph so it was 18 centimeters wide. So obviously each unit is 2 centimeters. So here's -3, -2, -1, and that would make... Oh, I can't have done that as I don't have enough space. Whoops, I went a little bit too far. So count that again. 1, 2, 3. And so I think that right here is my y-axis. Alright, let's put in all the important information. You remember that we had this vertical asymptote, so I'm going to draw this in as a dotted line. And the vertical asymptotes in an IB Studies exam or test or quiz will always be at x equals 0. Anytime you got a vertical asymptote, promise, it will be x equals 0. IB says so themselves. Alright, so we need to draw in the other important points. We've got, for example, the point 2, 9. So 1, 2, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, I'm going to count that again. Okay. And so I know that I come down off of the minimum and then I start going up again. Now if I want to make this a more precise graph though, perhaps I should enter the function into the calculator. And I'm going to look at the table so I can sketch a whole series of useful points. So I've got then the function 3x plus 12 over x squared. And I'll put it on the same window as they say here, a window that goes from -3 to 6, and then a y value going from -7 up to 15. Let's graph it. Yeah, it looks roughly like the sketch I'd already had. But I'm kind of interested, I suppose, in knowing what this x-intercept is. It would be good to indicate the x-intercept. So let's just find the 0 there. What is the 0 of the graph? So a left bound would be -2, a right bound would be -1, and I'm going to guess that it happens right in between at -1.5. It actually occurs at -1.59. So I'm just going to indicate that at -1.59. Oops. -1.59. I have an x-intercept. I'll just put its coordinates. So any important point is good to label with coordinates. That's point P, 2, 9. And I was kind of remiss earlier on in not putting in a scale, wasn't I? So let's just fix that problem. 1, 2, 3, 4, 5, 6, and -1, -2, -3, and -1, 2, 3, 4, 5, 6, 7. So from -7 all the way up to 15, right? Anyway, I'm going to go to the table now, second graph, and I'll look at the table and I can put in a whole series of more accurate points. Okay, whenever I'm graphing, it's good to put in as accurate points as I possibly can. So at -3, my y value is -7.667. It's a little off my my chart. At -2, I'm at -3. At -1, I'm at 9. 2, 4, 6. At 0, of course, it's undefined because it's a vertical asymptote. At 1, I'm at 15. At 2, I'm at 9. I already got that point. At 3, I'm at 10.33. Let's scroll down so I can see my remaining 3 values. At 4, I'm at 12.75. At 5, I'm at 15.48, so I'm already slightly off, and of course I won't be able to see me at 6. And so let's just smoothly connect the dots. And you end up getting a graph that looks like that. And I've indicated all of the important features: the label of the asymptote, the label of the minimum, and the label of the x-intercept. So that's a complete graph. Part G, on the graph I need to draw and label the tangent t. You remember that our tangent t was tangent to our curve at point P, and so our tangent was a horizontal tangent, wasn't it? So that's line t with equation y equals 9. I should do it with a ruler, shouldn't I? And lastly, it says that t intersects the graph of f at a second point. There it is. And we actually already know what that point is. We found it earlier on. It was -1, 9. But just to be certain, I'll say second calc intersect, and my first curve... Oh, I need to put in a second function. Alright, let's find the intersection of these two curves. So there's first curve, yes. Second curve, yes. And I'm going to guess that they intersect at -1. Am I right? Yes, I am. They intersect at -1, 9. It asks only for the x-coordinate, and so the x-coordinate is -1. And we're finished number 4.